Hi everybody, so in this video I want to talk about QQ plots, quantile plots. In particular, take a look at normal quantile plots, why we would use these, how we can read them, and so on. So to start, let's just consider the following data set for our textbook resampled data. There's a data set called NC Births 2004, and this data set contains 1,009 randomly selected babies that were born in North Carolina in 2004. And amongst all of the variables in the data set, one of them is weight. And this is telling the weight of the newborn baby in grams. And so we could create a histogram for this data set using the hist function in R. And notice here I've customized how many breaks we have. I added a title to the histogram and I changed the color of the bars. And so we can look at this data and we can see that it seems that the babies born were between 2,000 grams, 5,000 grams. Most of them were about 3,500 grams, 3,500 grams. And it seems like this data set is fairly bell-shaped, in that we have most of the babies born were in the middle, about average. And as we move away from that average weight, either greater or less than it, it's less and less likely that we have a baby that is born with a weight which is far away from the average. And so looking at the histogram, it appears that a normal distribution would be a good approximation for the distribution of weights. And one way that we can see exactly how normal our distribution is by creating what's called a normal quantile plot. So let's take a look at how that would go on the next slide. And so normally we would use technology such as R to create these quantile plots. We're going to create in particular a normal quantile plot. But it is maybe useful just to get a little peek at what the technology is doing to try and understand how to read them. So let's consider this data set, which is the births of newborn babies in North Carolina. A random sample of babies were selected. And what we can see here is I've lined up these values. These are the values in the data set. So the smallest weight in that data set was 1,928 grams. The heaviest baby that was born was 5,131 grams. And then we have a whole spread of values in between that. So the first thing we do is we note, okay, we had 1,009 observations in our data set. And then let's start at the largest value in our data set, which is the 5,131 gram newborn baby. And we can ask, well, what is the probability that a newborn baby is less than or equal to 5,131 grams? And so for our data set, for this sample, we would say, well, 100% of the newborns in our sample were less than that. But since we just have a sample, we should account for the fact that probably there are some larger values out there in the population that weren't picked in our sample. Not a lot of them, since 5,000 grams is already really, really large, but we should allow for the possibility that there are going to be some larger values in the population that weren't picked in our sample. So rather than say that this is 100%, instead we're going to add 1 to the sample size to just account for the fact that there might be some larger values in the population. And so rather than say this is 100%, we're going to say that this is 1,009 out of 1,010, which is very, very close to 100%. It actually comes out to 99.9%. And that is what we are calling P over here. So this is corresponding to approximately the percentage of all values in the population that are going to be less than or equal to this. And again, this is extremely large, so that's almost all of the population, but we do add 1 to the bottom to just account for the possibility that there are larger values in the population. And if you want to consider, well, how well does this distribution stack up to a normal distribution, we can then ask, well, what is the 99.9th percentile for normal distribution, standardized normal distribution? And so to get an approximation for that, we can use the qnorm function if we're working in R. So over here, I've got qnorm in goes the quantile that I have. So I'm going to do that precisely as 1009 over 1010. And we're using the standardized normal distribution. And R tells me that this is about 3.09. So this tells me if our sample X is a normal distribution, then this biggest value that we have in our data set over here, it should have a corresponding z-score that is 3.09. So this would be about 3 standard deviations away from the mean. So we're trying to map each of these values in our data set to what their corresponding z-score would be if the distribution were normal. And so we can do a similar trick for each of these values. So for example, this 5,046, it was the second largest value in our data set. So we could calculate what its corresponding quantile was in actuality. So it is 1008 out of this 1010. Then we can run the Q-norm function to get the corresponding z-score for what that would be if the distribution were normal. And we do this for every value in our data set, and this is why we use technology. So we would do this for all 1009 values in our data set. And so over here, I have the median value in the data set was 3,430 grams. So this would be right in the middle. 50% of the values are less than it, 50% of the values are greater than it. So that should line up with a z-score perfectly in the center. So that's why we have a 0 over here. And then for all of these values that are less than the median, all the way down to the very smallest value, since these are below the mean, they're going to have negative z-scores. And notice that normal distributions are symmetric, so it makes sense that we're getting the same values but negative when we go below the median value. And so for this particular example, we would call this a normal quantile plot, since we're trying to compare our data in particular to a normal distribution. Keep in mind, we could try and see whether our data resembles a different type of theoretical distribution other than the normal distribution. But since we were asking, is this newborn weight data approximately normal? That's why we are comparing our actual data X to z-scores from a standardized normal distribution. So we would call this a normal quantile plot in this case. And we can create these in R, since we don't want to go through this whole table ourselves, using the following commands. So this loads in the data set where all of these births are, which is called NC births 2004. And then the variable we're looking at is weight. So I do a quantile plot to compare our data with a normal distribution using QQ norm, input the data. We enter a second command, QQ line, which we'll see is going to help us interpret the resulting quantile plot. And so when I run these commands in R, you can verify out comes the following plot. And so let's make sense out of what is going on in this plot. There's a lot of information here. So what's being plotted are the value of, in our data set, the actual values. So in other words, the weights of the newborn babies, those are being plotted on the vertical axis. So those are going from like 2,000 up to 5,000. So from our smallest up to our biggest. And on the horizontal axis, on the x-axis, are going the z-scores, what we're calling Q sub pi. So these would be the corresponding z-scores of our x values if they came from a normal distribution. And the line down the middle is telling us how a normal distribution would look like. So if these dots are lining up on the line, that's telling me that the z-score of this actual value in our data set matches up with what the z-score should be for a standardized normal distribution. So for example, for this first smallest value that we have over here, it corresponds to this point right here. The x value is just about 2,000, and the y value over here, which is the corresponding z-score, is about -3. And then we go on to the next one, which is about a little bit over 2,000 and just a little bit bigger than -3. And that one would be represented over here. And we can go all the way out. I have a little bit too much over here. If you don't mind, let me just clear out this. that all the way out to the very last value would be right over here, where we have 5,000 with a z-score of about 3. And so at the most basic level, when I create a normal quantile plot such as this, if my dots are lining up close to this line or on this line, that means that a normal distribution would be a pretty good approximation for the distribution of my data. And if these dots are not that close to the line, then we need to be a little bit careful if we're going to use a normal distribution to estimate our data. So let's take a look at some cases where the data is not normal and how we could identify those features from a normal quantile plot. For the next example, let's consider the flight delays data set from the textbook. So this had data from over 4,000 flights operated out of LaGuardia Airport in New York City. And among the variables that were observed for each of these flights, one of them was a quantitative variable called delay. So this tells us the length of time that the flights were delayed in minutes. So we might want to think, would a normal distribution be appropriate for this case? So let's create a normal quantile plot, which is what's provided over here. So keep in mind, again, on the vertical axis is the actual variable that were of our data set, in this case, the delay time. And on the horizontal axis are what are sometimes called the theoretical quantiles, or these are like the z-scores for a normal distribution. And up here is just kind of what a standard normal distribution would look like. So we have this normal bell-shaped distribution. And the question is, well, is it reasonable that our delay time based on this graph would have a sort of normal looking shape? And the very short answer here would be no, this doesn't, because look, these dots are not falling on this line at all. So at its very simplest way of interpreting this would be if our dots line up on the line through the quantile plot, then it's normal. If our dots are not lining up close to that line, then it's not normal. So we could say that this is certainly not going to follow a normal distribution. And over here is actually what the data looks like. So keep in mind that these are the smallest values. These would be short delay times, and these would be really long delay times. So what this data set actually looks like is more exponential than anything else, if you recall back to what we talked about, exponential distributions. So over here, we can see that the most likely thing is that the flight is not delayed at all. And then as time goes on, it's going to get less and less likely that your flight is delayed 30 minutes. It's going to be less likely that your flight is delayed an hour. It's going to be even less likely that you get such a long delay as 2 hours. So hopefully from an interpretation and an intuitive point of view, you believe me that the data wouldn't be normal. The most likely outcome is no delay, and the longer and longer the delay becomes, the less and less likely that is to occur. So that's actually what we see in this data, flight delays for the variable delay. So over here, we have way too much stuff that's on the small end, and we don't have a lot of stuff in the middle. So this is very different from looking at the distribution over here. So let's see how we could read the dots in the middle in this quantile plot and actually see this histogram come out of that interpretation. So what we can see is that initially over this portion, you can see that these dots are a lot flatter than the line back here. And so when the slope of the data, the actual points of the data, are less than the slope of the line, so when the data is flat, that means we actually have way more data in our actual distribution than we would expect in a normal distribution. So this bar is way bigger than what we're actually seeing over here. Then as we move along, at some point over here, things seem to suddenly get much, much steeper than the line through the Q norm. And so for this portion of the graph over here, where things are pretty steep, This is telling us that these values over here are much more sparse than what we would expect at this point of the normal distribution. So we can read a quantile plot, and in particular, a normal quantile plot, by comparing kind of the steepness of the points of our data to the steepness of the line through the quantile plot. When our data is flatter than the line, like we have over here in this blue portion, that means we have more data in that bin than we would get in if it were normal distribution. When our data is about the same slope as the line, that means our data is approximately normally distributed. So this bar over here is about the same as this bar over here. Otherwise, for the rest of the data set, things don't match up well. Over this portion of the graph, you can see our dots are spread out. They're very sparse. We don't have a lot of data over here, and so the dots actually go up very steeply. And so when we have a very steep portion on a quantile plot, that means we don't have a lot of data over there. At least we have less data than we should have if the distribution were normal. So these are really nice plots. We can get a whole lot of information from looking at them, but we just need to be careful about how we read them. So that's the point of going through this video and the reading quiz that you're hopefully going to take a look at before our next class. So let's take a look at a couple more examples. Okay, so let's take a look at another example. And so here, the data, the actual data that we're looking at are average temperatures in Washington State in January. So a bunch of days have been recorded here. And it might be reasonable to think that weather is distributed normally. Most of the days are about average, and then sometimes we get some hot days in January. Sometimes we get some cool days in January. So you might suspect that your data would be normal. Create a normal quantile plot, and here's what it looks like. And so what we can see is there should be portions of the data which seem normal, but overall, a normal distribution would give us would be a bad fit, at least at these tail ends of the data. So let's try and unpack what's going on over here. So at first, we can see that over the blue portion, things are going up more steeply compared to, say, this line that's going through the QQ plot here, so the quantile plot. So over this portion, so over these portions of the normal distribution, our actual data set, our temperature data, is going to have less small values than we would get if it were normally distributed. So what we can see that initially for smaller temperatures, we have less observations. So it's even more unlikely to get a smaller observation than it would be in a normal distribution. Okay, next we hit this kind of portion that I've shaded green on the graph over here. And over this portion, the steepness of our data, of the dots in our actual data, pretty closely lined up with the steepness of this line. So over this portion, what we can see is that our data is approximately normal. So for, say, about here over to here, we should see that in the middle, our distributions should seem a bit normal in the middle. But then as we move out a little bit further, we can see over here, things start to flatten out. And so when we get this flattening, recall that means that we have a little bit additional data at the end of our data set. So this flat portion over here means that in actuality, our data set is going to have bars that are a little bit bigger than what the normal distribution would have. And so the textbook has these nice plots, which is where I got this one from, where we can kind of see these two distributions lined up with each other. And so over here, again, the observation is that for this portion where it's steep, we have less stuff than we would expect in the normal distribution. So these bars over here were lower than what we would expect in the normal distribution. These bars were about the same height as these bars over here, but then as we got out to the end, these bars were a little bit taller than what we would expect over here. And that's reflected by these dots starting to flatten out. And so this is what the histogram for the temperature data actually looks like. And so for some of the data, it kind of was somewhat normal, but out here it was too small. There should have been more, and over here there are too many values. So overall, normal distribution wouldn't be the best distribution to approximate the temperature data that we have in this data set. And so from the most basic analysis, you could observe that by saying, look, these dots that we have in the normal quantile plot are not lined up closely with this line. It's not normal. If somebody asks you, well, to explain why is it different from the normal distribution, well, then we can look and delve more deeply into the features of this graph and say, hey, look, over this portion where it's steeper than the line, then we can say that over this portion of values, our actual data set is more sparse than what a normal distribution. It's going to have less stuff than a normal distribution. Then it looks more or less normal. And then as these dots flatten out, this is telling me that our actual data set has more stuff in it than we would expect at the tails of a normal distribution. So to just summarize the examples that we took a look at, this first normal quantile plot over here, where it started off really, really flat and then became really steep, remember that was for the delay time, flight delay time. And we would say that this distribution is skewed to the right because most of our values are located on the left and we have a tail out to the right. So we describe the direction of the skewness of data, that is when data is not symmetric. We describe the shape in terms of the skewness in the direction of the tail. So since the tail is on the right side here, we say that this distribution is skewed to the right. More of the values are on the left, but again, we describe the skewness in the direction of the tail on the right. The next example that we looked at was the example with the distribution of January temperatures. And that histogram is down below. And so in this case, the data is skewed to the left. We have a tail on the left, and I can see that in the QQ plot. On the left side, the data is much more sparse because these dots are more steep. And then over here on the right, where most of the data is sitting, this has more data than a normal distribution would have on the right, and that's why we see this flattening out. So this middle histogram is skewed to the left because we have a tail over here on the left. And this last example, we haven't taken a look at this one, but this one you can see that for most of the time, this does line up being normal. So it seems like this graph, this histogram for this actual data set would be mostly normal, but it's going to differ on the edges. And if you're looking out over here, this is going up a little bit more steeply than this line is. So this is telling us our actual data over here is going to have a little bit more way out in this tail than a normal distribution. And for the same reason, this is increasing a little bit more steeply than this line is at first. So we have a little bit additional data in this tail of the actual data than the normal distribution does. So this distribution is symmetric. It looks the same on the left side as it does on the right side. If we had a normal distribution superimposed in it, the big difference is we're missing some stuff in the middle hump, and instead those values have been moved out into the tails of the graph. So we would say that these tails of the actual data are a little bit fatter than the tails of a normal distribution. So you've got a reading quiz, which is hopefully going to get you doing some practice in reading normal quantile plots.